So let me just start by thank you guys for joining today. My name is Matthew Chan. You guys can also call me Matt when you ask questions. Today we're here to talk about propeller design exploration, particularly with HEEDS. And I am the application engineer here at SDA Software. I am also the technical resource for computational fluid dynamics, CFD, and also for 1D system simulation. So let's get started. So this is today's agenda. You guys can take a quick look at it. I'll start with the company background, and then we'll slowly go through each topic individually. And at the end, I'll have a Q&A session. So if you guys have questions, you guys can feel free to put it in the chat, or you can save it at the end to ask me through the mic as well. So company background. So we are SDA Software. So our primary role is to provide software sales to your client, and we are Siemens value added PLM software reseller. We sell most of our Siemens products, including the CAE tools like VMAP, Star CCM Plus. We also have NX, Solid Edge, and also Team Center. And we also offers engineering services to our client. Majority of them are project consulting. So if we look at the right, we have some of the projects that me and my colleague had previously worked on. Our senior structural analyst worked on the Boom XB1 and the Dream Chaser. For me, I personally worked on the flying ship. I did their CFD simulation for this startup company. And a lot of times we'll also help our client to build complex models, right? When they need help. And sometimes they already have an existing models, and then we'll help them to do some extensive troubleshooting. Or when we have brand new customers, maybe they're switching from a different software, we do basic and advanced training also. So right now, I want to give you guys an executive summary for you guys to have the key takeaway up front. So in the current engineering landscape, if we look at this chart, a lot of different companies are in different phases of engineering. So on the far left, you have reactive phase, where you do a little bit more validation and troubleshooting. And maybe some companies are already like proceeded to doing more proactive engineering, where they do predictions with their VMAP, Star CCM Plus, doing their CAE analysis on their new products. And if we look at the vertical, that is the return on investment, what I also call ROI. And you can see that most companies just use a combination of CAE and CAD tools, somewhere between this reactive and proactive phase. But really, to maximize your ROI, because you already invest so many resources in the CAE tools, right? Then the way to do it is actually you move to the right, where you do a little bit more automation, automate these CAE tools, CAD tools, and do design exploration with HEEDS. So the first key takeaway for today is you can use HEEDS for any multidisciplinary optimization to innovate your product. And HEEDS is really strong at process automation so that you can save time and reduce time to market. So win you the race, or you just deliver a better product in general. So we'll demonstrate these 2 points through today's case study. We'll be going over a propeller blade optimization, and we chose this APC 10x5 fin electric blade as the thing to optimize upon of. And for the rest of the presentation, I'm just going to refer it as the stock blade, just too easy to keep track of. So you may wonder like why you should care about optimization, or even why HEEDS, right? Particularly when there's so many other optimization codes out there. Well, the first thing is you really want customization and performance improvement in your product when you're like going through generations and generations of product iteration or updates, because it really just translates to competitive edge in the market. Because the market right now is always looking for a better product or something more innovative. That kind of forces you to cater your product design to address market demand, right? So if you look at a lot of electric vehicle companies, they always have advertisement on how fast their car accelerate because that is the market expectation, right? They want a faster car, 0 to 60 faster, or maybe they're looking for a new form of transportation, like eVTOL. They no longer want to bypass the LA traffic with helicopters. Maybe they're looking at eVTOL, or they're looking at like air taxiing in the regional area. And we see a lot of those startup companies in the California. So basically, this is saying that seizing every opportunity to enhance your product performance, you will deliver a market-leading product so you can stand out among all your competitors or stand out from the vendors that industry you're in. So to me, why HEEDS is, I think HEEDS is really have strong four offerings for any users or analysts or like engineer like me, is that first of all is ease of use. Like HEEDS is really designed for all engineers and different discipline. Personally, I picked up HEEDS within a week, and HEEDS offers the search efficiently. You can get to an innovative design really quick with the proprietary Sharpa search algorithm that HEEDS offers. And HEEDS helps me to accelerate my productivity because I saved a lot of software development time using HEEDS because it streamlines a lot of my process automations. So I can just spend time on discovery and insight. Last but not least, the informed decision making, perhaps the most important one, is that HEEDS has a really efficient and in-depth post-processing capability that you can gain valuable insights so you can make your next decision on what do I want to optimize next, or what should I be focusing on when I'm looking at optimizing a propeller blade, for example. So I want to take a little bit deep dive on each of these offerings individually and show you what does that mean of ease of use, right? So again, HEEDS is designed for all engineers in different discipline because HEEDS offers something called portals for a wide range of commercial softwares. So if you're already an Abacus user, if you're a structural analyst, or you're like me, I am strong in my expertise in StarCCM Plus, there are these portals already in HEEDS where that allows you to do direct access and data transfer in and out those softwares. So those software will be just running in the background, but you can use HEEDS as an overlay and do a lot of stuff like optimization. So for example, I use a lot of StarCCM Plus, but when I import StarCCM Plus simulation files into HEEDS, I can now just change my automation setting in HEEDS. No longer, I don't need to run my own macros or interact with the API anymore. This really helps me save software development efforts whenever it comes to analysis automation for me. And now I can also update my simulation parameters when I'm doing my design iterations. I'm sweeping through maybe the sizing of a pipe, the length of a pipe, maybe the degree of the bend of a pipe, etc. Now I want to talk about efficient search that is offered by HEEDS. HEEDS helps you achieve the optimal answer, but it also does it in a really efficient fashion. This is all thanks to Sharpa, the proprietary search framework that HEEDS has. It is a hybrid approach. So when it comes to a very complex design space like you see on the right, there's a lot of peaks and valleys. Then what Sharpa will do, it will search locally and globally throughout the search. So for example, if I find this local minimum, it doesn't really get stuck there. It will still continuously search until it finds the global minimum. Well, you may wonder why this is important. Well, it gets quite remarkable when you change the vertical to cost. Suddenly, it makes sense for you that, hey, I want to chase the global minimum now because I want the minimal cost on this certain design or this certain product like this heat exchanger on the minimum cost on it so I can maximize profit. And what you're looking here is just the Sharpa search history of how it is probing the peaks and valleys in this complex design space. And once it finds or a suspect of the global minima, it's going to pull all those resources and data points around your global minima, try to find the absolute minimum. Now we just look at how Sharpa offers you the accuracy or how it drives to the absolute minimum. Now let's look at how efficiently that Sharpa or HEEDS can do it. So this is a plot or a graph for the benchmark result of maybe a complex design space of any sort. And the vertical here is an analogy, so just think about it as cost reduction, cost, whatever helps you imagine this. And horizontal is the evaluation number, just basically saying how many analyses you need to run to reduce the cost to a certain amount, by a certain amount. So if we look at this graph, we can see in the bottom, once again, we have this solid black line indicating the known optimal. And no surprise that only Sharpa and maybe genetic algorithm came close to the known optimal. But like I said, efficiency matters. So really for me, the area of interest is this early evaluation number area where you can have high return on investment, because to me, a lot of times I'd rather to get 20% improvement with 500 analysis versus 3,000 analysis get 22, 23% improvement. And you can see that in red here, that is Sharpa. Only a couple other algorithm came slightly close at very early evaluation number, but it falls off really quick. Only Sharpa provides that consistent search of improvement of your global minima. So now let's talk about how HEEDS can boost and provide you the accelerated productivity. To maximize engineering productivity with HEEDS, HEEDS will help you streamline process automation. It could reduce your software development time you need to spend on it. And now your engineer can just focus on discovery and insight. And this is particularly important when you have a multidisciplinary analysis process, because in the process you have all these different tools in the same in play, right? You have AIM-Sim, a 1D system simulation. You may have Nastran as of your finite analysis solver. And then the problem with this is the data transfer is really challenging because there's different APIs you have to learn. You have to know how to use them. And then it might be spanning across different coding languages. So for example, I know Java that is used in Source CCM+, but AIM-Sim is in Python. Then you need to correlate them, make it work. And a lot of times you got to do something I call like a technical char, where you got to like do your directory structuring. Where is this file exporting to? Oh, you have to import this from this directory, 2 folders up, etc. And even like for output file formatting is sometimes could be time consuming, because AIM-Sim could output a CSV file in a certain format, but it's not really readable by maybe Store CCM+, speaking from experience and pain. So the last thing I want to talk about is among the strong offerings of HEEDS, of course, is the informed decision making. So HEEDS is here to provide you the ability to compare and investigate performance in an efficient way. So I usually like using HEEDS to help me visualize performance trade-off, because it's quite strong at that regards. So if we look at an example, a trade-off study for maybe a structural design like the one on the bottom right, we can see that in the vertical, we have stress, horizontal, we have mass, and these data points really showcase quite clear relationship is when you reduce the mass of your structure, then basically you're shifting left, then your structure is experiencing more stress. Well, this might be easy to grasp from like basic engineering textbook, but when you extrapolate this to an aircraft where you have 30 parameters, now you have flutter, you have air elasticity, now you have drag, everything, then sometimes these sort of relationships is not as apparent as you want it to be. And this is where you can do this sort of study called Pareto front study in HEEDS. Another way that I would advocate and think is a hidden gem in HEEDS is that you can use HEED to assess variable importance. So HEEDS can help you generate this sort of importance plot where the vertical here is the importance, horizontal is your design parameter, and these tall bars basically are telling you how the design parameter is reacting or corresponding to certain study output. For example, if we look at the far right in this importance plot, we can see there's a tall blue bar. That is telling you that this design parameter is quite important when it comes to performance. And you can see there's also a green bar, so it's telling you this is moderately important to cost, but not as important to performance. So this sort of insight really helps your engineer to move on and proceed when it comes to building engineering intuitions or making next optimization decisions. Hey, what do I want to focus next? Sort of workflow. So now let's get into the case study to help you guys kind of picture or have an mental image of what this case studies are kind of going for. Is you can think of me as RC plane enthusiast. I want to have my RC plane to be better performed, has better performance, but I don't want to change anything else besides the propeller blade. And let's see how HEEDS helped me to do design exploration. So I explored the propeller design space with HEEDS. Basically, maybe I'm not a RC, maybe I'm not propeller blade experts, or maybe even though I am an expert, I can still use HEED to give me some guidance where I want to go, etc. Because HEEDS is not here just to toss you the best design, but you can also build engineering intuitions and expertise along the way and learn something from HEEDS. So as of any optimization or design explorations, I have a statement. So the objective here is to maximize efficiency at cruise. So you can think of me as a RC plane lover. I want to spend more time whenever I take my RC plane out as a better endurance. I can have more fun time in the park. And as any mission or project, you have requirements and constraint. In this case, would be the stock performance because I'm not willing to compensate for anything less than what it already is. So let's take a look at how HEEDS actually helped me do design exploration. So what HEEDS have is a performance history. Often it provides. If we look at this plot, the vertical indicates the performance of a certain design, and evaluation number is just the design that it is at, basically just the history of which design you're at right now. And in the bottom left, you have I have the 3D representation of the propeller blade. And HEEDS will basically search through different designs and evaluate performance after it modifies and do the performance assessment, and then it rate it with a performance, and you can see how the solid line is climbing. And that's what we call a best design history, is what is the best design at a certain point of time when it's doing the search algorithm. And at the end, it'll provide the best design. Now let's take a look what the best design came up to be and how much performance I gained from it. So I was able to get improved performance like thrust and power, and most importantly, better efficiency. So here we have the stock blade performance. Here just remember that the efficiency is like roughly 67%. No need to really pound on the thrust and power number. And for this blade, if we cut this blade along the short side, you will find out that each cross section of this blade uses the NACA 4412 airfoil shape. Basically, they are using the same shape, but they're different sizings. For those folks who are not really familiar with propellers. And then if we optimize it, this is what HEEDS provide at the end after I think roughly 500 iterations of design. I was able to get 4.5% efficiency improvement, roughly 4% improvement on thrust, 8% improvement on power. Overall, it was great. It came out, but we always have the next question. Can we do better than what we already got, even though it was great? We got 4.5%. So me being greedy, I added more parameters to the study. Like I said, the last batch or last optimization was running on the assumption of we can only use the same airfoil shape as the stock blade. But now I want to give it a little more degree of freedom. I gave it an airfoil database over for the airfoil shape. So now HEEDS has the authority or the autonomy to choose what airfoil shape it wants to use. So it turns out HEEDS was able to give me a much better blade, even compared to the last one was great. So in this latest blade, I was getting almost 6% thrust improvement, 9% power improvement, and for efficiency, what we care the most, we got 11%. So we're at 78% efficiency for this blade at a particular flight condition. And turns out, no surprise, that he did not choose the same airfoil shape as the stock blade. So as of all engineering problem, there's always a trade-off. And it's actually worth talking about because this will be a really important factor when you bring it back to your mission requirement, you bring it back to your system engineer. You got to talk about it with your other disciplines, see whether the trade-off is good or not. So let's take a look at it. So this is the efficiency plot that is comparing the HEEDS optimized blade versus the stock blade. In the vertical, we have efficiency. In the horizontal, we have what we call an advanced ratio. Basically, in this case, it correlates to the airspeed. So going back to the RC plane analogy, this is just saying the higher the number this is, the faster the plane is flying. So for us, we chose this optimization target to optimize upon on. So this kind of correlates to 22 miles per hour. So you can think of, I want my RC plane to be very efficient when it's flying at 22 miles per hour. And here we can see that the green is the HEEDS, green line and the green data points are the HEEDS blade performance or efficiency curve. And the hollow black point here is the experimental data for the stock blade. And like I just showed you, we got 11% improvement just from this point. And overall, we saw a much better improvement on efficiency at high airspeed, which helps me to have more fun time whenever the plane is airborne or at a certain airspeed, right? But obviously, there's going to be trade-offs. So the trade-off is at lower speed or airspeed, or when it's even on the ground, you actually maybe are consuming more power, or you're having less thrust as on the ground. So you're sacrificing maybe takeoff efficiency. And this sort of insight really helps your engineer or it helps your design team to understand, hey, whether this is something we can make, or is this something the customer is looking for? Maybe it's looking for an endurance aircraft, and this is great. This is what you want. Or we have a short takeoff distance. We can't really have a long takeoff distance, then this is a no-no. So it really comes back to the insight you gain from HEEDS. Now I want to talk about our in-house analysis process. We call it PropGen. This really is here to demonstrate how HEEDS is also compatible with open source and in-house software. From the couple slides before, when I was telling you about all the great things about portals, you might think that, oh, you need to have these softwares in place in order to leverage or make use of HEEDS, but really that isn't the case because I was able to do all of those with an in-house analysis process. No commercial software was involved besides my hard work. So it was comprised of basically just 6 functional scripts. And these scripts are just written in 2 different coding language. Majority of them are written in Python, and one particular script are in Julia. So I did embed 2 conceptual design tools in it to make this analysis process work. We have Xfoil for the subsonic airfoil evaluation. And then we also have, thanks to BYU Flow Lab, the CC Blade code for propeller evaluation. Now let's talk about how HEEDS helped me to automate the analysis process into something that again easy to use and repeatable. So right now I'm just going to show you this logical architecture. This is basically just almost like a system diagram of PropGen, the in-house analysis process. Might be a little overwhelming, but I'll walk you through it. So the biggest box here is the main system, PropGen. And of course, PropGen has 2 logical functions or functionalities, is that it needs to provide me the optimized prop geometry, the propeller blade geometry, and also needs to meet the engineering requirements. And basically, you can see these green boxes, they are the logical function of the corresponding systems. So, and when these 2 green boxes has green connection between them, it's just saying there's data transfer or there might be functional exchange. So if we look at the smallest box, that is our functional script. There are 6 of them, and I was able to consolidate them or group them into subsystem. And this is all done through HEEDS, because HEEDS helped me consolidate these functional scripts into what I call ease of use HEEDS studies. Because in HEEDS, even though there's no portal for in-house code, but there are portals for Python or even MATLAB if you use MATLAB. Then I can directly just import my Python script into HEEDS and use these portals, and these black arrows are basically just data transfer. So those green lines you saw, a green connection on that logical architecture, are just consolidated easily into just a single solid black arrow here. And for Julia, the only script that is written in Julia, there is no portal for Julia, but the generic portal is flexible enough that I can just use the generic portal and do a little bit of tagging, just choosing the right variables. It doesn't instantaneously recognize the variable, but it was not tedious at all. And the benefit after consolidating everything into HEEDS is that I can now oversee the entire workflow within HEEDS. So I can find all my input variable in the same place, whether they're from two completely different functional scripts, they're now in the same place. I can construct my output response like maybe thrust, evaluation, or the reference power, for example. I can compute or even just tag them in HEEDS, and then I can set my objective for my optimization, and then I can set my constraint at the same time. And what really this is getting to is it allows hands-off and code-free automation. So after everything is set up, I just need to lay back or sit back and have a live monitoring of what's going on, what is HEEDS doing. And this process is pretty quick for me. Like I did 500 design in like less than 14 minutes. And I think it was like 2 runs. And realistically, I didn't have time to really like sit back, but the story changed when you scale this up to other commercial tools, right? Like CFDs or stuff like that. So right now I want to talk about our engineering approach, and hopefully when you see our engineering approach, you can see how it could apply to your current workflow, or you can implement it for your future workflow. And we strictly kind of follow this process of we want to shift right on the engineering landscape because we want to maximize our ROI. So we'll start from the reactive phase and then slowly go through proactive and innovative. So in the reactive phase, what really matter is the validation and troubleshooting. You really need to finish these two things before you even move on to the proactive phase, because these two phases give you insight on your current design, where you have some strength in your design, there's some weaknesses, there are pitfalls. You can detect and screen them when you do validation and troubleshooting. And then after those are done, you can validate your design maybe with experimental data. And then what that gives you is engineering confidence that you can transfer to your proactive or predictive engineering phase. So when it comes to our validation, we chose this stock blade because there's a lot of public experimental data available, and even from the vendor. And we were able to cross-reference it with University of Illinois Urbana-Champaign's Propeller database. So we have a lot of confidence in the experimental data. So when we go ahead and did our validation for the stock performance, we have the numerical prediction in this chart in solid lines, and we have data points, experimental data points in data points. And we can see that the numerical result actually follow really closely to the experimental result. So we have really strong confidence that when we use this for our new designs, we can rely on it essentially. So moving forward to proactive phase. In this phase, really, we're just leveraging the validated methodology to do predictive engineering. Essentially, we're conducting numerical experiments on new designs or innovative designs or devices we want to add, right? This really just helps you forecast any potential point of failures in design, or even see the performance evaluation of these designs, whether it's worth going for, right? Maybe you get a 5% improvement, but cost went up 10%. It's just not worth it at that point. It just helps you to like kind of see where you want to go and take your design to. So for us, when we evaluated our new propeller designs, like I said, we're using CC Blade. CC Blade is great. It's a low fidelity tool that uses blade element momentum method, and it's particularly for propeller blade and turbines. The only thing about it that is, I would say, not really a disadvantage, but it is a script-based approach. it's not that easy to use. There's no really graphical user interface. So if we look at a CC Blade example script on the bottom right, everything is kind of like text-based. So that requires a lot of text swapping, text editing when you want to automate this tedious and time-consuming workflow. And of course, when it comes to innovative phase, I just let HEEDS take over and automated this workflow into the HEEDS study you just saw. And from that point, I only really need to interface with HEEDS variables. I don't have to touch the script anymore, except when I need to change or need to edit like functionality of the script, then that's different. And from that point, I really care about is what HEEDS offer me as post-processing, because I can now focus on discovery and insight. And one thing that I really like about HEEDS is that HEEDS offers you a really efficient way of looking at designs or screening designs. So this is what I call like a multi-pane view, where you can have multiple plots at the same time. This is nothing new, but they offer something called synchronous post-processing. So what does that mean? So if on the top left, I have performance history. If I select any particular design, the rest of the pane will automatically update based on that. So it makes sometimes when I want to screen certain design really easy, I click through them and then I get instantaneous know, oh, this blade design is, from my engine intuition, is like, okay, this is not manufacturable. Let's just screen it out. And I then take out the loop. This makes the process of looking at data pretty efficient. And there's different ways you can kind of cluster or like screen your data set or design sets. But that's a little bit more in depth. Maybe we'll talk about it in the future in the next webinar or something like that. But right now, I also want to talk about not just how efficiently HEEDS helps you post-process, but the depth it offers. So HEEDS really offers you a deep insight and discovery because it helps you have a better understanding of performance driving parameters. So if we look at the importance plot again, this one is directly on the propeller blade. We're going to see that now the top bars correlates with key performance indicator like thrust, power, efficiency. So to me, I can instantaneously spot what parameter is important to me whenever it comes to certain designs. Like, hey, maybe the top bars on the left, really, I really put more emphasis and take a look at it, what it is. And it gives me guidance when it comes to design explorations. And also another way to look at it is you can look at sensitivity between conflicting variables or non-conflicting variables. So this is kind of similar to the importance plot, but now the vertical is sensitivity. Sensitivity give you a little bit more sense of direction, but don't interpret it as which way it's going, but it just gives you a more stronger guidance in that sense, right? So we can instantly, again, spot the top bars, sensitive variables, and then I can see a confliction or something that raised my attention. Then it just drives me to, hey, maybe I should deep dive on what this parameter really is. Now, if I look at it, it's blade tip pitch angle. It makes sense now as a high sensitivity that this design parameter is introducing to this particular design. And he's really just not just toss you the answer, but it guides you along the way and build your engineering intuition when we're using it and leveraging it. So right now we're getting close to the end of the presentation. I just want to summarize a couple of key takeaways. So the first thing, maybe I sound like a broken record, but optimize your design to be the leading product and use HEEDS because a lot of times HEEDS offers you a lot of customizations. I was able to just use my in-house code. I don't need any commercial software, even though it would be better, and I can look at a lot of performance improvements or look at performance driving parameters to guide me through design explorations. He's also do reliability tests or studies. I didn't really touch on that, but it is there, so you can look at how like manufacturing imperfection can affect your design or like the impact of it. And last, you can look at the cost because HEEDS is so flexible. You can even just connect it to an Excel spreadsheet and it do your economic analysis and just let HEEDS drive your Excel math. And last but not least, definitely increase your engineering productivity through code-free process automation. Save your engineer software development time into these HEEDS studies so they can just focus on something else instead of writing scripts or writing like APIs or functions in their during their work time, you know. So I want to touch base on our upcoming webinar. It will be also on HEEDS, but this time we're actually looking at system designs. So the next webinar will be focusing on accelerating system design with HEEDS, AI Predictor, a brand new offering that HEEDS has, and in collaboration with AIMSIM on landing gear design for those folks in aerospace. Might be interesting. And this webinar will be focusing on how to achieve accelerated optimization. What we talked about is normal optimization, but with HEED's new AI simulation predictor, now this process can even speed up quicker. So now we're getting into the last slide. If you guys want to know more about us, you guys can visit our website. And if you want to take the discussion offline, you guys can also contact us through support at sdasoftware.com. And we are now offering free trials for HEEDS, and you can contact sales at sdasoftware.com as well. And on the right, we have the QR code. You can follow us on LinkedIn, and we always have our latest webinar announcement on there. Well, thank you guys for joining today. Thank you for your time. Feel free to follow us and learn more from our webinars. Thank you. Have a good day, guys.